When two engineers write code to solve the exact same problem, we need an objective mathematical method to prove which solution is superior. Let's examine these two C-style loop structures side by side. Algorithm A prints a value exactly n times, resulting in n total operations. Algorithm B executes twice as much work for the same input, running 2n operations. If we test both algorithms with a tiny input size, say n equals 10, the operational difference is negligible. Algorithm A executes 10 operations, while algorithm B executes 20. A gap of 10 operations takes mere nanoseconds to process. Scale that input to 1 million, and the absolute operational volume diverges aggressively. We are now looking at 1 million operations compared to 2 million. Measuring efficiency by simply counting operations creates an illusion of precision. It tells us how a specific piece of code behaves right now, but it fails to provide a scalable framework for predicting how complex logic will hold up under extreme data loads. If counting operations is short-sighted, measuring execution time in actual seconds is even worse. Standardizing physical execution speed across millions of different devices is physically impossible. This split screen compares two distinct computing environments: a modern supercomputer crunching 1 billion operations per second on the left, and a consumer laptop struggling through 100 million operations per second on the right. We will assign a highly inefficient quadratic algorithm, T of n equals n squared, to the supercomputer. Then we give a highly efficient linear algorithm, T of n equals n, to the slow laptop. This line graph plots their execution times as the data volume scales. Early on, the supercomputer masks its terrible algorithm with raw processing power. But as the dataset grows, the laptop's execution line inevitably crosses the supercomputer's path, eventually processing the massive datasets significantly faster. Raw hardware power cannot save inefficient architecture. To evaluate software properly, we must strip away the physical machine entirely and adopt a framework that measures logic in a vacuum. This is the purpose of asymptotic analysis. It is a mathematical system designed to measure the running time of code independently of all physical computing constraints. Instead of asking how fast a program runs right now, asymptotic analysis asks, what happens to execution time as input size scales toward infinity? By pushing n to the absolute limit, we isolate the algorithm itself. We completely ignore the programming language, the compiler efficiency, and the processor's clock speed. We are left with one critical metric: the growth rate. This defines the trajectory of how processing time increases relative to the incoming data size. Calculating performance at the theoretical threshold of infinity is the only objective way to ensure a database architecture won't collapse under tomorrow's traffic spike. Let's analyze T of n equals 5n plus 10. At a small input like n equals 10, the calculation is 50 plus 10. The constant influences the output. But scale input to 1,000, 5,000 plus 10 becomes just 5,000. The constant is mathematical noise. This scales to complex polynomials. Take T of n equals n squared plus 5n plus 20. Execute at n equals 1,000. The highest power yields 1 million, while lower terms barely reach 5,000. The n squared term dictates the trajectory. This gives us the rule of dominant terms. An algorithm's true behavior at scale is governed solely by its highest order polynomial. Everything else is ultimately irrelevant. Translating complex math into clean asymptotic notation requires a ruthless two-step filtering process. Isolate the highest power and delete all constants and lower-order variables. Take 4n plus 5. Drop the constant and multiplier to get O of n. For 8n squared plus 10n plus 1, erase lower variables and coefficients. The dominant term stands as O of n squared. Descending powers like n cubed plus n squared plus n instantly reduce to O of n cubed. If an algorithm takes exactly 50 operations, we strip the number entirely. Constant time is O of 1. By aggressively stripping away mathematical noise, engineers can instantly classify, compare, and rank the efficiency of completely different codebases. Every piece of software ever written falls somewhere on a universal hierarchy of algorithmic growth rates. This coordinate graph plots input size against total operations. In the highly efficient tier, we have constant time, logarithmic time, and linear time. As input grows, their trajectories remain flat, predictable, and manageable. But the inefficient tier behaves differently. Quadratic and cubic time curve sharply upward, and exponential time, O of 2 to the n, spikes in a near vertical line, consuming massive computational resources almost immediately. To see the impact numerically, look at an input size of exactly 100. A logarithmic algorithm completes the task in roughly 7 operations. An exponential algorithm for that same input size requires a number so large it breaks modern computational physics to resolve. The divergence on this graph is not a theoretical abstraction. It separates software that scales smoothly to millions of users from software that crashes servers the moment it hits production. These math curves map directly to everyday engineering. The highly scalable logarithmic curve is the domain of sophisticated search algorithms, like binary search, which cut massive databases in half with every